Got a question here about electrode potentials. It's got a bit about fuel cells in as well, and a little bit of acids and bases. So if I just read through the question and then give you some time to go through it, and then I'll go through the answers. So 3 redox systems in the table, C, D and E. So the half equations are shown. And then we've got 2 diagrams to process. So they're combining 2 half cells in each one to make a cell. And from the information in the diagram, we've got to work out the order of electrode potential, least negative at the bottom of the table, most negative at the top. Next part of the question, the redox system in D is put with a standard hydrogen half cell. We're told that the cell potential of the system is plus 0.34 volts. Given some information about the cell's pH, and then we've got some questions following. What's the pH of the solution in a standard hydrogen half cell? And then explain in terms of electrode potentials and equilibrium why the pH of the solution in the hydrogen half cell decreases as the cell delivers its current. And then we have to combine the 2 half cells to create the overall cell reaction taking place in the cell. Now we've got the part of the question that deals with acids and bases. So we're told that the cyanide ion is the conjugate base of a very toxic weak acid. In aqueous solutions of cyanide ions, an acid-base equilibrium is set up. Complete the equation for this equilibrium and label the conjugate acid-base pairs. And then in the next part, explain in terms of equilibrium why acidic conditions should not be used with cells containing Cn- aqueous ions. And now the question moves to fuel cells. It's not the hydrogen fuel cell, it's a direct ethanol fuel cell. So we're going to be given all the information required to answer the question. So we're told that these fuel cells are being developed in which the fuel is ethanol rather than hydrogen. The half equation for the ethanol electrode is given. And then some questions. One important difference between a fuel cell and a modern storage cell. One advantage of using ethanol rather than hydrogen in a fuel cell for vehicles. And then the overall reaction in this ethanol fuel cell is the same as for the complete combustion of ethanol. So we've got to write an equation for the overall reaction. And then from that, we have to deduce the half equation for the reaction taking place at the oxygen electrode. And then the final part of the question, using oxidation numbers, show that oxidation and reduction take place in a direct ethanol fuel cell. So first part of the question, we've got to look at the diagrams. So we've got the silver with the ammonia solution in. So that's obviously half cell C, and this one here is half cell E. The fact that this is the positive electrode is telling us that C is more positive than E. And then if we look at the next one, we've got the ammonia one again, the silver and ammonia one again here, so that's C. And we've now got silver ions and just silver, so that is D. And where's the positive electrode? It's this one here. So D is more positive than C. So in order of electrode potential, the least negative, i.e. the most positive, is D, then C, then E. So part B now, what is the pH of the solution in a standard hydrogen half cell? Well, that contains 1 mole per decimeter cubed H plus ions. pH is minus log H plus ion concentration, so the pH is minus log of 1, which is 0. Next part of the question, we had to explain why the pH of the solution in the hydrogen half cell decreases as the cell delivers its current. So I've got the two equilibria written up straight away, just to make sure I cover this part of the answer in terms of equilibrium. We know that the standard hydrogen electrode potential is 0 volts, so the E cell, the voltage of the cell, must be coming from this half equation here. So that must be plus 0.34 volts. So what is that telling us? It tells us that the silver ions are the more powerful oxidizing agent. They have the more positive electrode potential. So this equilibrium will move to the right, and therefore this equilibrium will shift to the left. That will generate H plus ions as the cell delivers its current, and so therefore the H plus concentration will increase, and therefore the pH will decrease. The equation for the overall cell reaction that takes place, well, again, I'm going to use these. I don't need to multiply any out because I've got the same number of electrons in each half equation. So this one proceeds forwards. So it's this silver ion plus a half H2 will make a silver atom and an H plus ion. The Cn- ion is the conjugate base of a very toxic weak acid. Complete the equation for this equilibrium and label the conjugate acid-base pairs. Well, we're told that this is a conjugate base, so this is going to accept a proton. So what will it become if it accepts a proton? It will become the acid HCN. And so this is one of the pairs. So we'll call this acid 1 and base 1. So this water molecule must be acting as an acid. So it will lose a proton, or donate a proton I should say, and become the OH- ion. So there's the other pair there. Explain in terms of equilibrium why acidic conditions should not be used with cells containing cyanide ions or aqueous cyanide ions. Well, if you put H plus ions into this equilibrium, which is what you've got, you would get the H plus ions combining or reacting with the OH- ions, and in terms of equilibrium, that's going to shift this equilibrium over to the right to replace those OH- ions. And what's it going to generate? The very, very toxic HCN. Last part of the question now, part D, all about fuel cells. So one important difference between a fuel cell and a modern storage cell. Well, fuel cells use external supplies of reactants, or you could say fuel and oxidant, whereas storage cells actually contain the reactants within them. An advantage of using ethanol rather than hydrogen in a fuel cell for vehicles: ethanol is a liquid, it's easier to store than hydrogen, and hydrogen has to be stored as a pressurized gas. It's very difficult to do that. So if the equation for this fuel cell is the same as the complete combustion of ethanol, well, there it is there. It's getting a bit trickier now. So we've got to deduce the half equation for the reaction at the other electrode in this fuel cell, so the oxygen electrode. So basically what we need to work out is when we combine the ethanol half equation that was given, there it is there, we need to combine that with something else to generate the overall equation. So we need to look at what's in the overall equation. What have we got in the equation we've already got that doesn't feature in here? That's got to be cancelled. And if there's anything missing, that must also occur in this other equation. So you can see in red there, I've got all the missing species there. So we'll just quickly run through it. We've got ethanol in the half equation. We need it in the overall, so that needs to stay. We've got 3 waters on the left, but we need 3 on the right. So we need to get rid of them from that side and generate 3 on the other side. So if we put 6 waters on this side, that's going to do that for us. The overall equation contains 3 oxygens, but we haven't got them at all in this equation here, so we need to put them in. We've got 2 carbon dioxide, so that's fine. We've done the waters. Right, so we need these H plus ions and electrons to disappear because they're not in the overall equation, so they need to go in as reactants on the left there. And then obviously that can be cancelled down further, so they would be expecting you to do that. So everything's divisible by 3, so there is the final answer. And then the final part, using oxidation numbers, show that oxidation and reduction take place in this fuel cell. Well, there's the overall equation there. The easiest one to do is the oxygen is reduced. Oxygen starts out in the O2 molecule as an oxidation number of 0, and then it's got -2 here on this side. So that is a reduction in oxidation number and therefore a reduction process. And you can see how I've written that up there. The carbon's a bit trickier. Now, carbon in ethanol is actually in the -2 oxidation state. So you can see I've got in pencil here an ethanol molecule, and I've put all the oxidation numbers in. So the hydrogen, nice and easy, +1 for each hydrogen. We've got 6 of those, so there's +6 from those 6 hydrogens. We've got an oxygen, which is -2. So from 2 carbons, we need -4 to keep neutrality in the molecule, and so each carbon must be -2. In CO2, it's +4. So carbon's the one that's oxidized. Its oxidation number changes from -2 to +4. It's pretty tricky, that one.